Okay, everybody. You had a lot of difficulty with this in class yesterday, so I thought I would go ahead and do this this first beam example for a video using virtual work. I mean, I gotta be honest, I was pretty surprised you had trouble even with just the basic beam analysis, finding the reactions, finding the bending moment diagram. Now, I know that you know how to do it. You did it in statics, you did it in 301, and you've got to be able to do it now. So I really encourage you to go back and review this. Same with trusses. You really have to be able to do trusses. So go back and watch the video for truss analysis if you're still having trouble with that one. But let's just do this one real quickly. I'll go a little bit fast, but for the video, you can stop and catch up with me, unlike in class. So hopefully this is a little bit better media for you. Okay, so we've got the cantilever beam. Cantilever just means it's fixed at one end, right? So I've got 6 feet over to point B, 6 feet again over to point C, and I have a uniform load. So it's pretty simple loading, right? I've already shown the moment reaction here at A. We also have vertical reaction at A, and this is very basic loading, so I know that the uniform load times the length is going to be 1 kip per foot times 6 feet, times 12 feet, so that's 12. Yeah, and then what do I do? How do I treat this to find the moment? I lump it into, let me bump this over, I lump it in to a resultant. The resultant is equal to 12 feet times 1 kip per foot, so that's 12. Right, that's where I get this to, same thing. But then this moment arm is 6 feet, so I have 6 times 12 is 72. So I have 72 kip feet for the reaction moment and 12 for the support, vertical support reaction. Okay, so from here, you should be able to find the moment diagram. Now, by the way, we're doing virtual work. Remember, we're trying to find deflections now using virtual work. So I'm going to need to write this internal forces, right? The internal forces are moment for beam. That's what we care about. So I need to write the MP system, the real forces, the real internal force in the beam is the MP system. And when I have this 72, it corresponds to negative internal moment, right? This is going counterclockwise, but clockwise is our positive internal moment on the left side, so that means negative 72. And then this is my shear, right? Maybe you want to write it down yourself, but right, the shear should look like this. The shear should look like this, 12 feet, 12, so this slope is 1. Oh, the slope is 1, we already know that from this. Remember, the loading equals the slope. This is the shear. Okay. So I have a positive value shear, means I have a positive slope. And then over here, I have 0 shear, so I have 0 slope. So I have a shape like this. Right? Now, if I want to find this as a function, I have a couple of options. What I pushed you away from a little bit at the beginning of class is method 1. That doesn't mean we abandon it forever, it just means I wanted to show you a new method, method 2. So we got to go back to using method 1, right, potentially, to write this one. So method 1 was just make a cut at x. So I make a cut here at x. I have this reaction, 72. I have this reaction, 12. I have my loading, 1 kip per foot. Right, this is my beam segment, it's x long. I have internal moment, MP of x, and then I sum moments, right? I sum the moments to find this unknown, or my equation, and I should end up with, right, I have plus MP, plus 72, plus MP, plus 72, plus the 1 times x over 2, right? This is 1 times x over 2, so that's where this comes from. Then 12x, because I have the 12, right? If I sum moments about this point, let's say I sum moments about this point, I get plus MP plus 72 plus the 1/2 x squared, that's from this part, and then minus 12 times x, right? 12 times x. Okay, so what I'm doing is just writing this out, but I'm already switching the sign. So I just kind of skipped a step there. This is the full equation, and then I'm solving it for this, right? MP. So MP of x is this one, minus 72. So that's my MP of x equation right there. Okay, next step is to do the Q system. I'm going to start with delta B. So this is Q for delta B. Here's point B. 1 kip. This one is also extremely simple, right? I should have a moment diagram like that. Minus 6, because this is 6 feet away. So my moment reaction is in the same direction. It's this way, right? 6, because it's 1 times 6, and then internal corresponds to negative internal moment. So I have this one. Now, this, you can make a cut the same way we did up here, but this is a very simple equation. It's just a line. Here's the y-intercept, and then I already know the slope is 1, right? From the shear diagram, I can find the slope. So, here, I'll write it over here. MQ is, y-intercept is minus 6, slope is 1, so it's mx plus b, right? mx plus b, that's what I'm doing here. Equation of a line, x minus 6. That's this one. So notice, from 0 to 12, right? 0 to 12, this is at 6, this is at 12, this is 12, right? Here's 6. But from 6 to 12, the Q system is 0. So when I plug these equations into my virtual work equation, this one here, right? Sum of the Q's times delta P's is equal to the integral if I go all the way from 0 to L, this whole section has 0 moment, so that whole section in the integral is going to be 0. So why don't I only integrate the 2 parts that I have? That makes sense. So I have 1 kip times delta P in this situation is delta B, because we put our dummy load at B. So I have B integral 0 to 6 of these 2 equations. Now I'm going to clean up the board so that I can write it out a little bit better. Okay, so now we're going to find delta B using the equation that was written down here a minute ago. So I have 1 kip times delta B is equal to integral 0 to 6. Remember I said from 6 to 12, MQ was 0, so I'm not going to bother writing it. X minus 6 times minus 1/2 x squared minus 72. Don't forget the 1 over EI. Now I can carry these out, right? X times this. I have 1/2 x cubed plus 12x squared, 72x, x squared, 72 again, and finally that one, I can bring my 1 over EI on the outside, keep my 1 kip, and delta B. Good. So, what did I do here? I simplified just a little bit, right? X cubed, fine, 12x squared, x, 72x, 6, right? 6 over 2 is 3, 6 over 2 is 3, 6 times 12 is 72 again, 6 times 72 is this one. Okay. So, now I just evaluate the integral. So, I have minus 1 over 8, x to the 4th. I'm going to go ahead and write, yeah, I'll write this at the end. It's all evaluated at the same distance, right? This one is 12 over 3, that's 4. This one makes 36, right? 72 over 2, 36. This is 3 over 3, so just x3. This is again 36. 36. And then this is just 432x. So all of this evaluated from 0 to 6. So all the zeros are going to be 0. Now I just put 6 in here. And I get 918 over EI. Delta B. Now, if you want to check this using RISA, you have to pay attention to the units. This works out to be, right, this one is moment, so it's kip feet. This is moments, it's kip feet. So kip feet times kip feet makes, this makes kip squared foot square, right? Then when I evaluate the integral, I get another foot square. To convince yourself, just look at this one. This should be in kip square foot square, then times foot, right? So I should have this, the product of this thing is kip square foot cubed. So that means this number is kip square foot cubed. And if I do this one, it's kip inch square, right? But I have that other kip here. If I bring it to the other side, then I end up with, right, because I got rid of it here, I bring that one kip over, the units work, oops, sorry, not inch. The units work out, so I get kip, so I have kip square, those go away, right? Then I should be left with, oh, I need to convert 1728 inch cubed per foot cubed. That gets rid of this, I have inch cubed over inch squared gives me inch. Right? It's always good to check your units because then you'll know if you made a mistake somewhere, right? Yeah, somewhere up here. You'll know if your equations are wrong. Okay, so if you want to plug that in, or sorry, plug in values here, right? Build your model in RISA and plug in your values. I used E29000, KSI, and moment of inertia of 100. And all of this makes delta B equal to 0, what was it, 547 inch. And sure enough, that's what I get in RISA. Okay, so next bit, I'm gonna do delta C. Okay, so now when I wanna go to find delta C, I have to use a new Q system. So my new Q system is one kip applied at C, right? One kip applied at C. So the moment diagram here is MQ. It's one kip times 12 feet. So I should have minus 12, right? So I have two options here. If you remember, the MP was something like this. Right? Parabola with negative 72 on the left side. Now, I can go ahead and do Q delta P. I can evaluate the integral here. Now, the full length has a continuous moment diagram, so I can take this equation, plug it in to MQ. I can take this equation and plug it into MP. And I can evaluate the integral just like I did in the last step. Or I can recognize that this is a nice simple shape, and this is also a nice simple shape, and I can use the product integrals. Where MQ is a nice triangle like this with a negative 12, and MP is a nice parabola that ends at 0. They both happen over 12 feet. All right, they're nice simple shapes. Now in the table, they're flipped, right? But that's okay. We can recognize that it's just a negative number here, it's fine. I can even mix it. If this is flipped, if this is positive and this one's negative, you can still mix it, right? But so find these on the table and you'll see that the integral from 0 to L for MP dx is equal to 1/4 m1 m3 times L. Now this m1 is this one here, right? This is m1, you'll see on the table, and this is m2, or sorry, m3 on the table. So let's just plug it in. So this one is, actually I can take this chunk and plug it in here. All I need to do is add the EI, so I can say 1 kip times delta C, right? That's my delta P is delta C now. Q is 1. Now I'm going to take this chunk and say 1 over EI. I'm going to pull that out of the integral. Now I have this one directly and that directly. I can plug them in, plug this piece in, times 1/4 minus 12 minus 72 times 12 feet. Done. I didn't have to do any integral. Super nice, right? If you evaluate this one, comes out to be, on the other sheet, sorry, on the other sheet, delta C is 2,592 over EI. Now the units work out the exact same as I explained before. You get this additional kip, but now look, it's very clear. Kip feet times feet. Oh, good, same. And if you plug in those same values in RISA, all right, E for steel, and I is 100, you get delta C 1.544. Yeah. And you'll see that that's the exact same. Okay, I hope this helps get you started on beams using virtual work on beams. Okay, so take a look at the next video to do a frame, right? It's the exact same thing, but now you just have different pieces. Okay, thanks.